you see the faces of millions of people carrying on with their daily routine in the bustling cities. All this could cease to exist in the blink of an eye by the power of something smaller than you and me. Hey there, let's start. Here we are. This is the atomic model proposed by Niels Bohr in 1930. This central portion is the nucleus. It consists of neutral particles called neutrons and positively charged particles called protons. In surrounding orbits lie the negatively charged electrons, which revolve around the nucleus at specific energy levels. They are held in orbit by the electrostatic force of attraction between the negatively charged electrons and the positively charged protons. The protons and the neutrons are held in the nucleus by the strong nuclear force. The width of the nucleus is up in the range of 10 raised to minus 15 meters, whereas the width of the atom is in the range of 10 raised to minus 10 meters. As you can see, the atom consists of a lot of energy that can be tapped into, but the size is very small, just like your
Anium. So here we have a pictorial representation of a nuclear fission reaction. Now nuclear energy can be harnessed by three different ways: nuclear fusion, nuclear fission and nuclear decay. But here we focus our attention specifically on nuclear fission because that's how we can controllably harness nuclear energy. Now here we have the reaction that leads to the release of energy. We have nuclear uranium-235 which has been hit by an accelerated neutron. That leads to an intermediate unstable state, uranium-236. The larger atom is now breaking down into two smaller atoms, namely krypton-89 and barium-144, with the release of three more neutrons which lead to the further chain reaction. Now what we see here is that there is a mass deficit between that of the larger atom and those of the smaller atoms. And it is that mass which has been converted into nuclear energy. We know of the famous equation E square equals to m square c to the power 4 plus p square c square. It is with that equation that we can calculate the energy released in a nuclear fission reaction. The mass deficit in this reaction is of the range 0.203 amu, and the average energy released in a reaction like this is 215 MeV.
As my significant other just mentioned, the process of nuclear fission occurs in the nuclear reactor. These are the control rods that absorb neutrons and curb the chain reaction. The heat energy that is released is then passed on to the heat exchange chamber, which contains a large reservoir of water. This water is then converted into pressurized steam, which is used to rotate the steam turbine. This steam turbine generates electricity just as any other mechanical generator.
So the efficiency of a nuclear power plant is in the range of 33 to 37%, which you might think is quite less. But consider the fact that energy released per atom is in the range of mega electron volts. So it's actually quite a lot. The nuclear power plant in totality is actually a very good investment in the long run. And also, it releases clean energy. Now let us move on to the next section and we'll show you some of the famous nuclear power plants.
The world's largest is the Kashiwazaki Kariwa nuclear power plant in Japan. It has 7 reactor units with a capacity of almost 8,000 megawatts. It was temporarily shut down following the 2011 earthquake and is yet to be restarted. The second and third largest nuclear power plants are the Bruce Nuclear Generating Station, situated in Canada, and the Kori Nuclear Power Plant, located in South Korea, respectively. Both have a net capacity of just over 6,000 megawatts. The debate over the largest nuclear power plant in India is between the Kudankulam nuclear power plant and the Tarapur atomic power station. This is because the former has reached its full capacity of 2000 megawatts only a few times during trials, whereas the latter has been consistent at 1400 megawatts. As a consequence of the famous Three Mile Island, Chernobyl, and Fukushima disasters, there was a need for damage control and accident prevention measures. The structure of containment needs the capacity to shield the outside environment, while ideal conditions must be maintained for the core via control rods and cooling. Proper disposal of waste materials needs to be implemented. Radioactive liquids are to be segregated, filtered, conditioned, and then diluted, while radioactive solids are disposed of in brick lined earthen trenches, RCC vaults, or tile holes. At all times, radiation levels of humans working inside the plant should be monitored. Lastly, an emergency response plan can save lives in the case of an accident. If the safety measures are in place, nuclear is arguably one of the cleanest sources of energy, and in their brief history of existence, nuclear power plants have changed the world.